Okay, thank you, and thank you for giving me the opportunity to present my work here. This work was actually published already in August this year with, guess, with this nice picture of the week from ESO. The red actually shows our nice ArTéMIS observations, but you can see over here we actually can do a bit better than that. But before going into what caffeine is and research we did with it, I want to motivate the work a bit. And to do so, I will summarize some important results from the Gold Belt survey. You will realize why we start from the Gold Belt survey, and then I will change to caffeine. Okay, one of the obvious results that came from Herschel, but it was also known before, the interstellar medium is highly filamentary, a lot of elongated structures, especially the cold interstellar medium. And that was perfectly mapped with Herschel. Looking into the Gold Belt survey and all the Gold Belt clouds, there was this famous result that filaments typically have a width of around 0.1 parsec with like a factor of 2 plus or minus. This is like observed again and again. There's also some doubts, but typically we can figure out where the observational problems were for this. Then another very important result from Gold Belt survey is that the prestellar cores are actually mainly lying in these dense filaments. It's about 75%, depending on the structure a bit. But we see that like these filaments must be responsible for the bulk of the star formation in the ISM. And we can even go a step further and then look how much of the gas from the cloud is actually ending up in these cores. And we can look at this depending on the column density. And we can see that, well, it's actually rapidly rising at around like 8 times 10 to the 21 particles per centimeter square, or AV of 7. And then it's basically like a flat line for higher column densities. And the final result is then actually, if you compare the core formation, the core mass function and the IMF, we do find that there is quite some similarities. And if you compare, there's like the core mass function shifted to something like 20 to 40% higher masses. So this gives you another efficiency that is happening in the transitioning from cores to stars. Obviously, there's also, again, some uncertainties in all of this. But based on all of these observations, there is, well, mainly Philippe André was coming up with this filament paradigm for star formation, which basically says that, okay, we have large scale compression of the ISM, and they will create filaments. And these filaments are typically dense and are in a thermally critical, transcritical or supercritical state. In a supercritical state, they often then supported by magnetic fields, some internal turbulence, so they have enough time to fragment into prestellar cores. Based on this scenario, one can then make some kind of predictions. One is that the typical filament width is about 0.1 parsec. We've seen this in the nearby galaxy, but we still have to test this a bit further out with high resolutions. James Webb will be one option here. Then the core mass function is supposed to shift to higher masses for higher line mass filaments, which there is some observational evidence for this, but this also needs to be studied in more detail. What I want to focus on is actually the last point, that the star formation efficiency will be constant above a certain threshold, which is basically a direct result of what we've seen so far. But what do I mean with star formation efficiency? So star formation efficiency, as we define, is the star formation rate above a column density divided by the cloud mass above this column density, where we define, where we derive the star formation rate. Typically, it's used from class 1, class 2 YSOs within these contours, and we derive the mass and therefore calculate it, and then we go to higher and higher column densities to see how this evolves with the denser gas. We're not the first one having this idea. There has been like relatively recently still, this Pockerel et al. Paper. However, they were measuring the star formation efficiency per freefall time. So this epsilon FF, which is a measurement that comes from the turbulence-regulated star formation scenario based on Krumholz papers. And what they find is that the star formation efficiency per freefall time is actually quite constant. And this would contradict the filament paradigm, actually. But we thought, well, so this would contradict so why do we actually do the research? And then we're like, okay, let's compare the different scenarios. And we see this turbulence regulated scenario will give us this blue line, while the filament paradigm is showing this curved structure. And we see in this low mass, low density regime, they actually, like, this cannot differentiate between the two scenarios. So what is happening at this higher density regimes? And that's where caffeine is coming into play. So caffeine is the core in filament formation and evolution in natural environments survey. It targets all the high column density areas with more than 40 magnitudes visual extinction within 3 kiloparsecs from the sun. That's roughly, or it's 80 regions with about 5.5 square degrees. The idea is then to use this data to derive high spatial dynamic range column density maps without any saturations, which saturation is an issue in some of the Herschel maps. The observations were done with the ArTéMIS camera at the Apex telescope, and it observes in parallel 350 and 450 micron, which gives us resolution of 8 or 10 arc seconds. Most of these observations coming from ESO large programs, which were in total 288 hours. However, ESO left Apex in 2022, so since then observations are a bit tricky, and we are basically done with 2/3 of the observations. So more information about caffeine you can find on this webpage here. So this is now then what we get as observations. Up here is the ArTéMIS observations. This is 350 micron. As you can see, we only observe the dense small-scale structures. Spatial filtering is here an issue. So therefore, we then use this data and make use of the similarities to Herschel to actually combine these data with it's basically like a feather approach. It's the IMRAD emerge command for Myriad, which we use for most of the data. However, there's also a second approach, the Scanamorphous, which is a bit more sophisticated, but therefore takes a bit longer time. So this data will come with time. Then we get already some nice intensity maps. And then we use even more of the Herschel data to do SED fitting for each of the line of sights. And we get nice column density maps for all of these regions. In a final step, we then combine these high-resolution column density maps with only Herschel column density maps to recover all of the larger scales and to make sure that we actually have all of the cloud within our maps. So we get some multi-resolution column density maps. They have in the high resolution, it's 4 times higher than the normal Herschel column density maps. And we kind of resolve this 0.1 parsec out to about 3 kiloparsec. We also correct saturations. As I said, Herschel has, especially in the high mass star forming regions, quite some issues with saturations, but we have now estimates where we can correct for this. All of these data products you can find on the ESO archive. So if you find these maps interesting, have a look. It's everything there, and we will update it with more and more data with time. Then for this study, as we are looking within the galactic plane, there's a lot of line of sight contamination. So we try to correct for this using 13CO data from different line surveys like SEDIGISM, Galactic Ring Survey, and THRUMS. And then because in this study, we were mainly interested in the high density areas. So we only look at regions that have sufficiently enough dense gas over a certain area. So we end up with a subsample of 45 fields. This takes account of like 75% of the observing time that we have so far. Now, deriving the star formation rates is, of course, a big issue for these distance clouds. So we use two approaches. One is based on the High-Gall clumps that we have in these maps. There's this relation for star formation rate from Elia et al. This works quite well, especially because there's towards the higher densities, as the clumps are always tracing these higher positions. But then we also use classical YSO counting. However, these are distance clouds, so we miss all of the low mass YSOs. Therefore, we fit the mass of the YSOs based on their spectral on their spectra. Then fit the mass distribution and assume an IMF to recover all of the low mass elements, and then get an estimate for the star formation rate from there. Now we have masses, we have the star formation rate, so we can finally actually look at the star formation efficiency. And as you can see, we have these two different methods, but both of them predict are relatively in agreement, and both of them predict a flat behavior between, well, 10 to the 22 and 10 to the 23 particles per centimeter squared. Obviously, on the higher end, we're limited by statistics, so we don't have enough sources to derive the star formation rate. On the lower end, the confusion within the line of sight, and also the fact that we don't get closed contours for estimating the mass is the limiting factor there. But that's already a quite good result. And if we now compare with the models, we actually see that this prefers the filament paradigm for star formation compared to the turbulence regulated scenario. But we've seen, like in the nearby clouds, we are more sensitive to this lower mass regime. So we calculated the star formation rates by simply counting the class 2 YSOs, and we get this green line, which fits quite well in this picture. And we have some data points from other studies, and everything seems fine. But there was something like the Pockerell paper, were they completely wrong, or what is going on? So we were like, okay, they used class 1 YSOs, so let's see what happens if we use class 1 YSOs. Well, we pretty much recover what they were doing. But we see this yellow line is actually way more in agreement with the turbulence scenario. So that left us puzzled for a moment. So let's leave caffeine for a small moment and have a look into what's happening here in between, between the class 1 and the class 2. What's the difference between class 1 and class 2 YSOs? We know that the class 1 YSOs are younger. And well, what we then did, instead of having this cumulative star formation efficiency estimates, we actually derive it per column density bins, so like between two contour line. And what we see is the class 2 YSOs actually go way more into the diffuse gas and the lower density gas, while the class 1 YSOs are sitting more in the dense gas. And on top of this, we actually see that the class 1 YSOs, they start showing up actually just around this 10 to the 22 particles per centimeter squared. And if you remember from the beginning, that's actually what we've seen in the High-Gall data already, that the core formation efficiency starts to rise exactly at this column density. And this threshold of star formation is actually something that has been seen in many studies before that already. So this is not something new, but it fits quite well with this filament paradigm of star formation. So actually there's not too much of a contradiction here. So then what we came to conclude is that these class 1 YSOs, they're sitting more in the dense gas, but they're also younger objects. So most likely they decouple from their environment and start to move into the lower density gas. So they are likely to be the better tracer, but also measuring star formation rate on the class 1s can be a bit more tricky. It's more uncertain because the evolution time is dependent on the class 2 estimates. but definitely something to keep in mind when doing these kind of studies. Another thing that that was raised by especially people that do models, star forming models, they said like the star formation efficiency should be way higher, at least in some parts of the process. But if you assume that star formation is actually more of an episodic event, so there's a bunch of stars form at some point, and then it's getting more quiet again, and then they form again. But we are averaging over a large selection of clouds. These are all different evolutionary phases and so on. So even if the star formation efficiency would be higher in some time frame, then we would not see it in such a average. So this would just vanish in the data. So therefore, we are quite happy with this result. And therefore, I'm going for the summary. So I showed you the CAFFEINE survey, which observed 80 dense molecular clouds within 3 kiloparsec from the sun. We created unsaturated multi-resolution column density maps with 4 times higher resolution than the normal Herschel data. We find that the average star formation efficiency is essentially constant between 10 to the 22 and 10 to the 23 particles per centimeter squared, with a star formation efficiency of around 5 times 10 to the minus 8 per year. In the nearby clouds, we find the class 1s the class 1 YSOs are mainly concentrated on the high column density above 10 to the 23 particles per centimeter, which shows this threshold of star formation. And therefore, in overall, this is in better agreement with the filament paradigm for star formation. And now going ahead, we got some nice James Webb dust absorption data, and we found that the CAFFEINE data is actually quite good in calibrating the large scale column densities that you get from this data, because James Webb field of view is kind of small. So this will be a major application of this data as well. And yeah, thank you for all of you for listening, but also special thanks to all of the ESO staff and APEX staff, which are very important to doing this kind of large and long-term surveys. Thank you.